Hey YouTube, Benjamin here.
And Kilian, what's the most populated place on the planet?
Are you thinking Russia? China? Perhaps India?
It's actually right beneath our feet.
Interesting. Well, as it turns out, a single teaspoon of ordinary soil contains more microbes than there are humans on the planet. And we've trained them to do some pretty neat stuff.
But before we talk about that, we need to talk about something called biocatalysis. It's a catalytic action of a living organism to convert one chemical into a completely different one. This takes place using a series of enzymes, special proteins which work as a reusable catalyst for a staggering number of reactions, with each enzyme being responsible for the conversion of one specific chemical into another very specific but different chemical.
Many enzymes are often linked or loosely grouped in such a way that they form a long series of enzyme reactions, called a metabolic pathway, where the product of one enzyme reaction becomes the reactant of the next, which becomes the reactant of the next, and so on. This whole process allows a cell to quickly convert chemicals into a completely different final product at the end of a metabolic pathway.
These pathways are often self-regulating, where the creation of the final useful chemical inhibits the enzyme which starts the metabolic pathway. Effectively, this allows a cell or organism to create only as much product as it needs. Metabolic pathways are brilliant little systems that are essential for life. They allow for thousands of unfavorable but useful reactions to occur and support the life and growth of a cell.
Metabolic pathways are used primarily as a means of breaking down food and supporting energy generation in cells, as well as synthesis of things a cell might need to survive, such as toxins to defend itself. Microbes also produce waste products as a consequence of metabolic action. However, some microbes have a dirty secret. There are specific species of microbe that can break down and extract out metals as a byproduct of some of their metabolic pathways. And we've found a special niche for this unique trait, helping us in our own mining industry.
Microbes with this property were discovered in 1951 when a microbiologist, Kenneth Temple, discovered bacteria in a highly metallic soil. Upon further investigation, these bacteria were shown to experience greater growth in highly metallic environments. That's because they were eating the metal. It's the utilization of bacteria such as these which led to the advent of biomining.
Biomining is a relatively new mining method. It's used in conjunction with traditional mining to increase the yield of target metals from ore and reduce the possibility of things like acid runoff from discarded ore and mining debris. Whilst traditional mining methods are useful and efficient in extracting out most of the target metal, biomining using bacteria allows us to extract almost all remaining metal from the waste. This makes biomining increasingly useful, both as a mining process and for environmental protection.
There are many different species of bacteria which are able to extract metals as part of the metabolic process, but the genus Biomining is one which is particularly adept at the extraction process, so it constitutes a large amount of species which have this utility. The trait which allows them to do this is an enhanced ability to oxidize the elements in the various metal ores, for example converting iron 2 to iron 3 in the species Biomining trioxidans. This species can also convert sulfur to sulfate, whilst other bacteria can only extract a single compound.
The species of bacteria we use is massively dependent on the ore in question we are mining. Bacteria benefit from the oxidation of the elements and compounds we wish to extract by undergoing reduction in other areas of the cell. This oxidation reduction produces energy for the cell as well as nutrients the bacteria needs to survive. This is a prime example of what we call direct leaching, where the bacteria is in direct contact with the waste ore.
The alternative leaching method in biomining is indirect leaching. This is where the bacteria produces chemical leaching agents as a waste product, which we then use to treat the ore. The bacteria itself is not in direct contact with the ore at all, but it's cultured to produce oxidizing agents, which will aid in the element compound extraction. But where do these two methods actually take place? What's the infrastructure we need to support it?
There are 4 methods which we currently use in biomining. These are dump leaching,
Heap leaching,
stirred tank bioreactors,
and in situ. Dump leaching and heap leaching are most similar methods. Both methods involve irrigating piles of waste ore with dilute sulfuric acid to attain metal ions in solution. Bacteria or bacteria-derived chemicals are then used to treat these piles of waste ore, extracting oxidized elements and compounds into the sulfuric acid irrigation for collection. Whilst most methods essentially use large piles of waste, heap leaching is a slightly more refined method in that the ore is ground into finer powder and mounds of material are aerated, and this aids in reaction time and oxidation.
On the contrary, stirred tank bioreactors are large tank or vat setups that contain a community of microorganisms and the ores and metals of interest. This method is currently used commonly for gold extraction. It is a useful method in that it can assist in the separation of specific metals. For example, it is used in Uganda, where it can separate cobalt from copper mine tailings.
By comparison, the in situ method is relatively new and is looking like the most promising method for future ore extraction once we've exhausted all the other areas which are easier to mine using traditional methods. The in situ method basically works by pumping a solution of sulfuric acid and ore extracting microbes underground into ore deposits, then sucking the solution back up out of the soil for filtering and further processing to access the metal.
In all four methods, the microorganisms only extract the elements and compounds into the solution. All of the actual processing and precipitation to obtain purified samples of the metals is done afterwards and is a purely chemical process. These processes are mainly used for metals such as iron and copper, as well as uranium, gold, silver, and cobalt, and to a lesser extent, nickel and zinc. Based on our current metal use and the market demand for metal, biomining is only likely to become more popular. It also has implications in pollutant processing and recycling, as the ability to reprocess waste metal from junk will give a new lease of life to pre-used metals and reduce heavy metal toxicity in the environment.
As it stands, the dirty little secrets of these special microbes actually have a lot of potential for making our lives and the mining industry cleaner and healthier in general. And it's a testament to the success of green chemistry that biomining and associated processes are being implemented and taken seriously.
Traditional mining still has its place, but when augmented with biomining, it is more productive and better for the world we live in. And that can only be a great thing.